All right, so let's talk about the air. The stuff we breathe all the time.
It's more than just empty space, that's for sure.
Yeah, like it's this huge system, right? It controls our weather, and it helps make life possible.
It really does. I mean, the atmosphere, that's what we call this layer of gas surrounding the Earth. It regulates temperature, and it protects us from harmful radiation from the sun.
So we're talking about a pretty important topic here, right? I think it's really cool to understand what's going on up there, especially when you see a big storm or something like that.
Absolutely. I mean, understanding the basics of the atmosphere helps us understand so much about our planet and the world around us.
Exactly. So in this episode, we're going to break down what the atmosphere is made of.
Oh, we'll take a look at the different layers.
Yeah, we'll also discuss the difference between weather and climate and how those two are connected, but not the same thing.
Of course. And we can't forget about the water cycle.
Right. And then we'll delve into how air masses and fronts create the weather patterns we see every day. And then we'll wrap things up by talking about some of the craziest weather events out there, like hurricanes and tornadoes.
All right, let's get started then.
So first things first, what exactly is the air we're breathing made of? Like, what's in it?
Well, believe it or not, most of the air we breathe is actually nitrogen, about 78%.
Nitrogen? Really? I always thought it was mostly oxygen.
Well, oxygen is the second most abundant gas. It makes up about 21% of the atmosphere, which is essential for us to, well, breathe and live.
Oh, yeah, duh.
And then that last 1% is a mix of various other gases, like argon, carbon dioxide.
Oh, and water vapor.
Yeah, exactly. All of these gases play a role in how our atmosphere works.
So it's this whole mix. I mean, it's not just one thing. It's a whole bunch of stuff up there.
Exactly, and they all kind of interact with each other.
It's okay. We've got the ingredients. Now let's talk about those layers you mentioned earlier.
Sure, we can think of the atmosphere as having these distinct layers, kind of like layers of a cake.
Okay, I like that analogy. So what's the bottom layer, the one we're hanging out in right now?
That's called the troposphere, and it extends from the Earth's surface up to about 12 kilometers, or about 7 miles high.
7 miles. That's pretty high.
It is, yeah. And all of the weather we experience happens in this layer, like all those storms, rain, snow, clouds, all that stuff happens in the troposphere.
So it's pretty much the most active layer.
Oh, definitely. It's also the densest layer, meaning that most of the atmosphere's mass is concentrated here. You'll also find most of the atmospheric water vapor in the troposphere, which is what forms our clouds and precipitation.
And the temperature of the troposphere, doesn't it get colder as you go higher up?
It does, yeah. The rate at which the temperature decreases with altitude is called the lapse rate.
Lapse rate. Okay. I've never heard that term before.
It's about 6.5 degrees Celsius per kilometer, or about 3.5 degrees Fahrenheit per 1,000 feet.
Wow, so that explains why mountaintops are often covered in snow, even when it's warm down here.
That's exactly right. And commercial airplanes, they usually fly near the top of the troposphere.
Oh, why is that?
Well, they do that to avoid a lot of the turbulence that happens lower down in the atmosphere, where you have a lot of weather patterns forming.
Ah, makes sense. Smoother ride that way.
Right. So above the troposphere, we have the stratosphere. It extends from about 12 kilometers to 50 kilometers.
Okay, that's a pretty big layer.
It is, yeah. And one of the most important features of the stratosphere is that it contains the ozone layer.
The ozone layer, yeah, that's the one that protects us from those harmful UV rays from the sun.
Exactly. It absorbs most of the sun's ultraviolet radiation, which can cause skin cancer and other health problems.
Mm-hmm.
Now, here's a fun fact. The temperature in the stratosphere actually increases as you go higher.
Huh. That's weird. Why does it do that?
Well, it's because of that ozone layer we were just talking about. It absorbs the UV radiation, and that warms the air.
So it's almost like a shield, and it's getting warmer as it's protecting us.
Yeah, you could think of it that way.
That's pretty amazing. Okay, so what's next? What's above the stratosphere?
Okay, so the next layer is called the mesosphere, and it extends from about 50 kilometers to 85 kilometers above Earth's surface.
Okay, the mesosphere. What happens there?
Well, the mesosphere is actually the coldest layer of the atmosphere.
Oh, wow. How cold are we talking?
Temperatures can drop to as low as minus 90 degrees Celsius or minus 130 degrees Fahrenheit.
That's freezing.
It is, and this is also the layer where most meteors burn up upon entering Earth's atmosphere.
Oh, the shooting stars.
Exactly. The friction between the meteors and the air molecules in the mesosphere generates heat, causing them to burn up and create those streaks of light we see in the night sky.
So the next layer is the thermosphere. And I'm guessing from the name it's probably pretty hot.
You got it. The thermosphere is the hottest layer of the atmosphere, with temperatures that can reach up to 2,500 degrees Celsius or 4,500 degrees Fahrenheit.
Seriously, that's like ridiculously hot.
It is, but the air density is extremely low. So even though the temperature is high, it wouldn't feel that hot if you were up there.
Okay, so it's hot but not dense. What else is going on in the thermosphere?
Well, this is the layer where we find the International Space Station and many other satellites orbiting Earth.
Oh, wow, so it's not just about temperature. It's also a very active region for space exploration.
Exactly. And another interesting thing about the thermosphere is that it's home to the ionosphere.
The ionosphere, what's that?
It's a region where solar radiation ionizes atoms and molecules, creating electrically charged particles called ions.
Ions, okay. And what do those ions do?
Well, they're really important for radio communications because they can reflect radio waves back to Earth, allowing for long-distance communication. The ionosphere is also where the auroras occur.
Oh, yeah, the Northern Lights. I've always wanted to see those.
They're really amazing. They're created by the interaction of charged particles from the sun with the gases in the thermosphere.
So that's 4 layers down. What's the last one?
Okay, so the final layer of the atmosphere is called the exosphere, and it extends from about 600 kilometers outwards, gradually fading into the vacuum of space.
So that's like the very edge of our atmosphere.
Pretty much, yeah. It's the least dense layer of all, with very few air molecules present.
So if you go past the exosphere, you're basically in space.
You got it.
Wow. So we've traveled from the ground all the way to the edge of space just by talking about the layers of the atmosphere.
It is pretty amazing, isn't it?
It is, and I think it's a great way to understand how much is going on up there. You know, it's not just air. It's all these different layers, each with its own unique characteristic.
Right. It's very complex.
Now let's talk about something that people often get confused. Weather and climate. What's the difference?
Well, think of it this way. Weather refers to the short-term atmospheric conditions we experience at a particular time and place, like temperature, humidity, precipitation, wind. Those are all elements of weather.
So like when I check my phone to see if I need an umbrella, that's weather.
Exactly. Climate, on the other hand, refers to the long-term average weather patterns in a particular region.
So it's the big picture view.
Yeah, it takes into account things like the average temperature, precipitation, and wind patterns over a period of many years, usually 30 years or more.
This climate is more about the trends over time.
Right. Like if a region has a climate that's generally warm and humid, that means that over many years, those have been the prevailing conditions. And it's influenced by many factors like latitude, altitude, proximity to oceans.
So it's not just a random thing.
No, definitely not.
And both weather and climate are influenced by this really important process, the water cycle. Can you explain how that works?
Sure. So the water cycle is essentially the continuous movement of water on, above, and below the surface of the Earth, driven by the sun's energy and gravity.
Okay, so the sun is the engine.
Pretty much, yeah. So the cycle starts with evaporation, where liquid water from oceans, lakes, rivers, even from the soil, is heated by the sun and turns into water vapor.
Water vapor, that's like invisible water in the air, right?
Right, you can't see it, but it's there.
And then what happens?
Well, that water vapor rises into the atmosphere, and as it rises, it cools. And as it cools, it condenses back into tiny water droplets or ice crystals, depending on the temperature. And these droplets or crystals clump together to form clouds.
So evaporation makes clouds.
It's a key part of the process, yeah. And then when those clouds get heavy enough with all that condensed water...
It rains.
Yes, or snows, or sleets, or hails, depending on the temperature. That's called precipitation.
Ah, okay. So the water comes back down to Earth.
Right, and then some of that water that falls as precipitation flows over the land as runoff, eventually making its way back to oceans, lakes, and rivers.
And the cycle just keeps going.
Exactly. It's a continuous process.
It's pretty amazing how it all works together.
It really is. The water cycle is fundamental to life on Earth. It distributes water and heat around the planet and influences both our weather and climate patterns.
So, okay, we've got the water cycle down. Now let's get into the nitty-gritty of how weather patterns are formed. And this is where those terms air masses and fronts come in.
Right. So an air mass is a large body of air with relatively uniform temperature and humidity.
Okay, so it's like this big chunk of air that all has similar characteristics.
Exactly. And these air masses can form over different parts of the Earth, like over land or over water, and that determines their characteristics.
So if an air mass forms over, say, the cold Arctic Ocean, it would be cold and moist.
Mm-hmm. That's right. That would be a maritime polar air mass, or MP for short. If it forms over a warm tropical ocean, it would be warm and moist. That's a maritime tropical air mass, or MT.
What about air masses that form over land?
Well, if it forms over a cold continent, like, say, Siberia, it would be a continental polar air mass, or CP, which is cold and dry. And if it forms over a warm desert, it would be a continental tropical air mass, or CT, which is warm and dry.
So you got these four main types of air masses. Maritime polar, maritime tropical, continental polar, and continental tropical. And these air masses, they don't just stay put, do they? They move around.
They do, yeah. They're constantly moving and interacting with each other.
And that's what creates fronts, right?
Yes. A front is the boundary between two different air masses.
So it's like a clash of the titans.
In a way, yeah. And when these air masses collide, it can cause some pretty dramatic weather changes, like sudden shifts in temperature, wind, and precipitation.
So the different types of fronts.
Well, there are four main types: cold fronts, warm fronts, stationary fronts, and occluded fronts.
Okay, let's start with cold fronts. What happens there?
Well, a cold front forms when a cold air mass advances and pushes underneath a warm air mass. The cold air is denser, so it forces the warm air upwards.
And what does that cause?
This rapid lifting of warm air can lead to the formation of thunderstorms, heavy rain, and sometimes even hail. After a cold front passes, the temperature usually drops and the air becomes drier.
So those sudden downpours we get sometimes, those could be caused by a cold front.
They could be, yeah. Now, a warm front is the opposite. It forms when a warm air mass moves over a cold air mass.
So instead of pushing underneath, it rides over the top.
That's right. And because the warm air is less dense, it rises gradually over the cold air. This usually results in more widespread and gentler rain, or sometimes snow if it's cold enough. After a warm front passes, the temperature rises and the air becomes more humid.
So if you've got like a steady rain for a couple of days, that could be a warm front.
It could be, yeah.
Okay, now what about a stationary front?
Well, a stationary front occurs when a cold air mass and a warm air mass meet, but neither one is strong enough to push the other out of the way.
So they're just like stuck.
Pretty much, yeah. And this can lead to prolonged periods of cloudy skies and precipitation, sometimes for several days.
So those long stretches of dreary weather might be caused by a stationary front.
It's possible, yeah. And finally, we have occluded fronts.
Occluded fronts, those sound kind of complicated.
They can be a bit more complex. An occluded front forms when a cold front overtakes a warm front.
So it's like one front chasing down another front.
That's a good way to think about it. The weather associated with occluded fronts can be a bit mixed, but often includes precipitation and changing temperatures.
So fronts are basically these battlegrounds where different air masses collide and create all sorts of weather for us.
Yeah, that's a good analogy.
So now let's talk about the really exciting stuff. Severe weather, like hurricanes, tornadoes, thunderstorms, the really wild stuff.
Yeah, so severe weather events are caused by extreme atmospheric instability, where you have a lot of energy in the atmosphere and rapid changes in temperature and pressure.
So it's like the atmosphere is going a bit haywire.
Kind of, yeah. So let's start with hurricanes. These are massive rotating storms that form over warm tropical waters.
And they can be really destructive.
Oh yeah, they're some of the most powerful storms on Earth. Hurricanes are characterized by their very low central pressure and incredibly strong winds that can exceed 157 miles per hour. They're also associated with torrential rainfall, storm surges, and tornadoes.
And they're ranked on the Saffir-Simpson scale, right?
That's right. Category 1 hurricanes have the weakest winds, while Category 5 hurricanes have the strongest and most destructive winds.
Like Hurricane Katrina in 2005 was a Category 5 hurricane.
Yes, and it caused widespread devastation.
Okay, now let's talk about tornadoes. These are those terrifying spinning columns of air that come down from thunderstorms.
Yes, tornadoes are much smaller than hurricanes, but they can be even more intense. They can have wind speeds that exceed 200 miles per hour, which is just unbelievable.
I mean, you're not kidding. That's enough to rip houses apart.
Absolutely. And they form when there's a lot of wind shear in the atmosphere, meaning the wind is changing speed and direction with height.
So it's like the wind is getting all twisted up.
Yeah, and that can cause the air to start rotating. And if that rotation becomes strong enough and touches the ground, you've got a tornado.
And those are ranked on the enhanced Fujita scale, right?
Yes, it goes from EF0 for the weakest tornadoes to EF5 for the most powerful ones.
Now let's move on to thunderstorms. Those are probably the most common type of severe weather we experience.
Yeah, they are. Thunderstorms form when warm, moist air rises rapidly into the atmosphere. As the air rises and cools, the water vapor condenses and forms those towering cumulonimbus clouds.
Those are the big puffy clouds we often see before a storm.
Right, and thunderstorms are characterized by lightning, thunder, heavy rain, and sometimes hail and strong winds.
So how does lightning form?
Well, lightning is a giant spark of electricity that occurs when there's a separation of electrical charges within a thunderstorm cloud.
So it's like static electricity on a massive scale.
Yeah, pretty much. The thunder we hear is the sound produced by the rapid heating and expansion of the air around the lightning bolt.
So it's all connected.
It is, yeah.
Yeah.
And then we have two other types of severe weather that are a bit different: droughts and floods.
Those are kind of like opposites.
They are, yeah. A drought is a prolonged period of abnormally low rainfall, leading to a shortage of water.
So it's like the opposite of a flood.
Exactly. Floods occur when there's an overflow of water onto land that's normally dry. This can be caused by heavy rainfall, melting snow, or storm surges from hurricanes.
And both can have devastating consequences.
Absolutely. Droughts can lead to crop failures, water shortages, and wildfires, while floods can cause property damage, displacement of people, and even loss of life.
So it's really important to be prepared for all types of severe weather.
It is. And understanding the science behind these events can help us better predict them and prepare for their impacts.
So all this stuff we've been talking about, why is it so important for people to understand? Like, why should we care about the atmosphere and all its quirks?
Well, for one thing, understanding the atmosphere allows us to predict the weather. And that's important for so many things, like agriculture, transportation, even our daily lives.
Right, like knowing if you need to pack an umbrella or if your flight might be delayed.
Exactly. But beyond that, understanding the atmosphere helps us understand our planet better. It helps us study climate change, air pollution.
And it helps us prepare for natural disasters.
Absolutely. By understanding how the atmosphere works, we can develop better early warning systems for severe weather, which can help save lives and property.
So it's not just about knowing whether it's going to rain tomorrow. It's about having the knowledge to make informed decisions about our future.
Exactly.
I think it's pretty amazing that we've learned so much about the atmosphere.
Yeah.
And that we can use that knowledge to protect ourselves and our planet.
It really is a testament to human curiosity and ingenuity.
So now that you know a little bit more about the atmosphere, the different layers, how weather works, here's something to think about. What are you most curious about? Maybe you're wondering how scientists predict hurricanes, or maybe you're fascinated by the northern lights.
Maybe you want to learn more about climate change or air pollution.
Whatever it is, we encourage you to keep exploring, keep asking questions, and keep learning about the amazing world around us.
Thanks for joining us.
Thanks for listening.